a rule fit a problem that you're given, why not try to make the problem fit a rule, right? And what I mean by that is, don't be afraid to manipulate it a little bit, right? So if I need to change its look, so I have 1 over x to the fourth, I can rewrite that as x to the negative fourth power. All right. So the antiderivative of x to the negative fourth, it's the power rule, just in reverse. So yesterday we talked about this. What you're going to do is increase the exponent by 1. All right, so that's going to become x to the negative third. Now there's an understood coefficient in front of the x, an understood coefficient of 1. We're going to divide that coefficient by the new exponent. Right, so we're looking at 1 over negative 3. The only thing that, it's pretty common error, people forget the plus c. So the only thing that you really have to worry about at this point is not forgetting that plus c. Right. Now you can clean it up if you want, but it's not necessary. Right. We've talked about this enough throughout the year. I don't really believe in simplifying without a purpose. Simplifying for simplifying's sake is really just something for algebra 1, maybe algebra 2. Now it's like, if there isn't a clear goal in why you're simplifying, then what's the point? All right. In the case of number 2, we have 4 separate functions that we can anti-differentiate. So we have the 3 to the x, we have negative e to the x cubed, and we have that x to the e power. And that x to the e is my attempt at making like a trick question, because it looks like, because you see an e in there, it looks like it might be exponential, but it's actually a power function, right? So, well, actually, I don't need the funky s anymore. We're going to take the antiderivative of each function separately. And just for this one time, I'm going to kind of go a little crazy and show all the intermediate steps, but you'll see how you can consolidate and not have to go too crazy every time. So when you take the antiderivative of 3 to the x, the rule for that is to rewrite and divide by the natural log of the base. Antiderivative of the e to the x is going to be e to the x, but before we do that, the 3 to the x over ln of 3 has its own plus c. All right? So the constant of integration comes from each one of these terms being anti-differentiated. All right? So then I'm going to have a minus e to the x, antiderivative of e to the x is e to the x, plus I'm going to have a difference c. So I'll call that c sub 2. All right. X to the third, anti-differentiate, increase the exponent by 1, becomes x to the fourth. Divide that understood 1 in front of the x by that new exponent, becomes 1/4. But that gets its own constant, c sub 3. And then the last one, x to the e power, increase the exponent by 1. And again, that's what I was saying. It's my little attempt at a trick question. If you compare the third and fourth functions to one another, you see that they're pretty much the same, except this has an e as an exponent versus a 3. Well, e is just another number, 2.718-ish. All right? So you follow the same principles here. Increase the exponent by 1, divide by the new exponent. All right? So plus 1 over e plus 1, x to the e plus 1, but that's going to also get its own plus c, c sub 4. All right, so I'm just going to color code here a little bit. That is not a highlighter. Undo. All right. So I can consolidate my constants by adding them all together. What kind of number am I going to get when I add 4 constants together? A new constant, yeah. All right, so I'm going to have 3 to the x over ln of 3 minus e to the x minus 1/4 x to the 4th plus 1 over e plus 1 x to the e plus 1 plus my new constant, which, since it's the only constant in my expression, can just be c. But if you wanted to make it c sub 5, you could do that. You're not going to lose credit for, bless you, twice. You're not going to lose any credit for giving a constant a subscript. That's not anything anybody's going to care about. All right. Number 3, 5 times the cosine of x. All right. This one we talked about yesterday as being associated, or this type of problem, having a constant multiple that can be factored out. And we spent a lot of time learning about derivative rules in the first semester, and there was a reason for that. Because if you have a good understanding of derivatives, then antiderivatives becomes a whole lot easier to handle. You know, when I teach Calc 2, the biggest issue I have is the fact that most of the students didn't have me for Calc 1, which means that they didn't have the same kind of, or at least my kind of emphasis put on knowing derivative rules. So when they get me as a teacher in Calc 2, there's an expectation that, you know, they know certain things. And you're like, where is this coming from? Like, my former students, like my Calc 1 into Calc 2 students, when I say, what's the antiderivative of cosine of x dx, even if they haven't seen the notation before, they're like, it's the sine of x. And then I say, why? Well, because the derivative of sine is cosine. Whereas the students that didn't have me, they're like, well, where'd you get that? It's like black magic. Right? Knowing your derivative rules is the key to understanding your antiderivative rules. So if that's something that you've been a little weak on throughout the course, it's never too late to make it a point of emphasis. So when people are saying, when I ask, what is the derivative of tangent, and they reply, secant squared, without any hesitation, if you're one of those people who are like, how did that happen? How did you get that? Then take a little bit more time and review those rules, because it will make a difference. All right. So 5 times the antiderivative of cosine, like I just said, is sine of x, but really plus c. So 5 times all of that, which is really just 5 sine of x plus 5c. But 5c is really what? Just a c, right?
Just a C,
All right, it's still a constant multiplied by a constant. All right, number 4 we did yesterday, I believe, just on a different app. So we'll get there. 5 through 8, they're all actually pretty easy to integrate or anti-differentiate. It's just they're kind of in disguise at first. Number 6 and 7, I have no idea why I did this, but they have parentheses in them. They don't really need the parentheses, so I'll take that as a typo if somebody needs that. But number 5, since we haven't learned anything related to handling a quotient and its antiderivative, like, you know how for derivatives we have a quotient rule. Here, you know, I'm sure there is a quotient rule. There is no quotient rule per se. There is a method or set of methods that you could use to find the antiderivatives of quotients. All right, so I don't know how else to say it than that. It's just like when I say that there's an entire course dedicated to the study of antiderivatives, it's for stuff like quotients and products and things like that, right? Because it's kind of a case study analysis, you know, like in this situation you do this, in that situation you do that. It gets pretty intense, right? But here, what I'm going to do is just simplify by breaking up the fraction. Basically, what I'm doing is I'm taking something that's unfamiliar and making it into something that is familiar. Like we just got through working with the power rule for antiderivatives. So why not see if we can make this fit the power rule, right? In order to do that, we break up the fraction, simplify, little keep the base, subtract the exponents. And then for each one, increase the exponent by 1, divide by the new exponent. All right, divide the understood coefficient. In the first case, there's just the understood coefficient. The other ones, it's explicitly stated. All right. I don't know why. Why can't I effectively select the highlighter tool? It's just a me thing, I guess. All right, so increase the exponent by 1, -2 becomes -1. Divide 1 by -1, you get a -1 x to the negative first. Now, I don't have to write the plus c here because I know that ultimately all my plus c's are going to come together to make 1 plus c at the end. All right. Increase my exponent by 1, -3 becomes -2. Divide 2 by -2, you get a -1. You don't have to write the 1 if you don't want, but I'm just doing it to show the result of the calculation. Right. -4 becomes -3. -3 divided by -3 is a +1. X to the -3rd, all plus c at the end.
Maybe I missed this before, but why is there all added together? Why is it just +1c? Wouldn't it be like plus like c? Since it's like c plus c plus c.
Because
Well, basically, what we learned yesterday was that it stands for constant, and basically, although you can have, like, you have different ones as a first equation, you only need to use 1c, because it doesn't, like, have, like, a numerical value, so having, like, more than one, it doesn't matter.
Okay.
Is that it?
yep,
That was pretty good right there.
pretty solid.
That, wow, that was big, guys.
Yep.
You just, whoa-wee.
So number 6 is actually, I don't know, it's not the easiest one on the whole page. It's probably second from the top in terms of easiest problems. First thing I'm going to do, and you wouldn't have to do this, is just, and honestly, this problem's been like this for like a cool decade. I don't know why I put the parentheses there. I do know why I haven't removed them. I'm just lazy. Or I have been lazy. But I don't know. But it's still the same idea. Increase the exponent by 1, divide by the new exponent. But again, that's, and there I am doing the same thing again. I'm applying the power rule in reverse, but only for power functions. So 1/3 x cubed. The issue that I found is that, and this is not indicating anything for anybody in here, because there's the guilt effect. Like anytime a teacher would say something that is like, and people, they're not listening, they're not doing that, they're not paying attention, I'd be like, he's talking about me. You noticed I was not paying attention. I'm not saying that, but what I will say is that people who don't always pay attention, they get to this point and they're like, all right, I understand calculus. And then I go on to the next one and write that the antiderivative of secant squared is tangent of x. And they're looking at it like, okay, I guess I'll worry about that later. But why is that not 1/3 secant cubed? Right? Because if all we're going to do is increase our exponent by 1 and divide by the new exponent, then shouldn't that be the case anytime we have an exponent? Yes and no. There are techniques that allow us to do that for trig functions, but the first and foremost, the idea that you want to have in mind is what function has a derivative that is equal to this function, all right? So if I'm looking at secant squared, I'm asking myself, if I take the derivative of a function and get secant squared, what must that function be? And you say tangent, because the derivative of tangent is secant squared, all right? So you don't want to fall in love with just one technique, and that's what I was saying. The people who don't always pay attention, they get the power rule and they say, okay, well, I'll just do that for everything. Well, you can't, because it's not always going to work. Right? So you got to make sure that you're staying on board with each different type of technique. Also, just keep in mind that everything that we're going to learn, you already know how to do. So it's kind of weird to think about this. You know, when we're taking derivatives and antiderivatives, you already know how to do everything that we're going to be covering. It's just a question of how we're applying that knowledge. Right? So, like in this case here, number 7, radical x plus 1 over 2 radical x. Okay, that looks like nothing we've seen before in the context of an antiderivative. But if I rewrite it as x to the 1/2 plus 1/2 x to the negative 1/2, just by a slight algebraic manipulation, it's now a perfect fit for the power rule. All right, it doesn't involve trig, doesn't involve any other crazier functions, exponentials or logs. So it's just straight up power function. Increase your exponent by 1, x to the 3/2. There's an understood 1 as a coefficient. If I divide 1 by 3/2, what am I going to get? 2/3. All right, it's going to be the reciprocal. All right. X to the negative 1/2, add 1 to that, you get x to the positive 1/2. That one's much easier because I'm taking 1/2, dividing it by 1/2, and I'm going to get a 1. So plus, you could just write x to the 1/2, or you could tuck the 1 in there, it doesn't make a difference. Plus c. All right, so you see how easy that was in comparison to what it looked like initially. It looked like a nightmare initially, but cleaning it up a little bit took a lot of the sting away. Also, be mindful of the fact that how you clean it up is very important, right? Because I looked at this and said, okay, well, let me write it in power form. If you looked at this and said 2 fractions, let me add them together, I need a common denominator, you could actually make your life more complicated by doing that, all right? Later on in the course, I'll show you a really, really beefy way of handling something like number 8. It'll take like a page of work. It's not a method I'll expect you to know how to do. It's just me. Like, yeah, more like reasserting my dominance as the alpha, the pride.
Oh.
You know, it's really like that.
On that one.
Yeah, it's like, yeah, I run this show. You know, so.
Watch out, MC.
But the easy way of handling it is to use basic algebra 1 and say, well, 2t squared minus 1 squared, I could just distribute that out. Now, if it's 2t squared minus 1 raised to the 7th power, I don't want to distribute that out, although you could use Pascal's triangle. Get ready for that. That's going to make a comeback soon. We'll go over it, though. 4t to the 4th minus 4t squared plus 1 dt, and now it's simple power rule. All right, so increase your exponent by 1. I think my battery needs a charge here. T to the 5th, divide by my new exponent, so 4/5. T to the 3rd, divide by my new exponent, so 4/3. And the constant value is kind of weird. It's really not difficult because it's either a rule or you're actually just using the power rule again. What a lot of people will do, because they just forget, is they just tuck in a t to the 0th or x to the 0th, depending on the situation, and you just apply the same idea. It's a power relationship. Right? So increase your exponent by 1, t to the 1st, divide by your new exponent, 1 divided by 1 is 1. At a minimum, it's a justification for why the rule works the way it does. But Right? Some people just kind of use it as I don't want to call it a crutch because it gets the job done, but you know, they rely on it as a method to solve the problem. So really it's the idea that if you have a constant, you multiply it by whatever the variable is. Right? But we'll get into some more geometric ways of looking at that down the line. All right.